They still have a bit of a stiltedness. Yeah.
Welcome to Think Science. I'm Nathan Cohn with Texas Public Radio. At each of these quarterly talks of Think Science, our goal is to get you in and out in an hour, having learned a little bit more about the topic at hand. And our focus today is on new frontiers in space exploration. You're going to learn about the search for life on Mars and the future of how we'll continue to work on the red planet and elsewhere. We'll hear about what we've learned from geological missions and the lunar and Martian surfaces. And finally, you'll see a vision for what could be when it comes to our future spaces, living spaces on the moon and maybe elsewhere. And we'll see how San Antonio could be in the forefront of this development. Today's presentation is not only streaming live on Facebook and YouTube, but it will be archived so that you can later share it with your friends or family, or maybe your children or grandchildren, to inspire them in their career path and choice, because there's likely to be something that will inspire the next generation of future scientists in today's talk. Each of these great presenters will offer an overview of their work or research, and I know what they'll have to say will spur some great questions, which you'll be able to ask today as well. Whether you're watching on Facebook or YouTube, all you have to do is write your questions in the chat on either Facebook or YouTube, and when it comes time for the Q&A portion of today's broadcast, we'll present your questions to the presenters today. Finally, today's Think Science presentation is made possible by UTSA Knowledge Enterprise, by Port San Antonio, and by you as a supporter of Texas Public Radio. Let's hear from our first presenter today, who is Dr. Danielle Wyrick, a planetary geologist with a background in structural geology, volcanic tectonic interactions, and fluid gas migration through fractured systems. Her research includes quantitative and qualitative analysis of the origins of geologic and tectonic features and processes on terrestrial planets and their satellites. She has experience in comparative planetary geology, remote sensing, regional tectonics, and fault growth and fracturing processes. And last year, the Geological Society of America recognized Dr. Wyrick with the Ronald Greeley Award for Distinguished Service for a continuing commitment to helping early career scientists succeed by providing professional opportunities and ensuring recognition of their efforts. So congratulations on that, Dr. Wyrick, and welcome. Thanks for being here today.
Thank you. I appreciate the opportunity to talk with you and the San Antonio and surrounding area listeners. I just wanted to make a quick note that I'm a local. I went to school here, and I really want to share some of the cool space science that we've been able to do locally. And so just to jump right into it, some of the research that we're doing here in San Antonio covers the entire solar system from Mercury out to Pluto. And don't have time to talk to it at all. So I'm just going to focus on some of the stuff that I personally have worked with. And importantly, one of the main targets that I've recently been looking at is our own moon. One of the reasons why we're interested in the moon is simply it's close. It is our closest target for exploration. Now, we understand now that the moon's history has been a kind of tumultuous. It started with a giant impact formation. Something hit Earth early on, and the remnants became our moon. Even after it had solidified and come together, we still had later stage volcanism, these eruption of the mare basalts, as we call it, and that's the dark regions that we see on the moon. And then for the last 3 to 4 billion years, it's been bombarded over and over again. The moon lacks an atmosphere, so every meteorite, no matter what size, will create a tiny little crater on the moon's surface. And we actually use this cratering record from the moon to date all other planetary surfaces. And so this is one of the main areas that we are looking at as scientists and as engineers of where can we really head next. And one of the major tools that we're using on that is the Lunar Reconnaissance Orbiter mission. Now, this mission has been orbiting the moon for over a decade. It carries a large suite of instruments that have looked at the moon through almost every wavelength, from visible to infrared to ultraviolet. We've sounded it with radar, and we've detected neutrons on its surface. And all of this data together is telling us a lot of really good information for our next steps of exploration. I always like to throw up this. This is the temperature map of the moon. So as it cycles throughout its day, which is approximately 28 Earth days, the temperature on the moon really goes from very, very cold to very, very hot over time. And so when we think about how we might explore the moon, we need to take into account these major temperature fluctuations. And probably one of the most tantalizing findings that we've had in the last few years is that there's the potential that there may be water ice on the moon. At the north and south poles of the moon, there are deep enough craters that at the bottom of those craters never see sunlight. We call them permanently shadowed regions. And within those permanently shadowed regions, if a water molecule from a comet or any other delivery makes it into that crater, it has no energy to leave. And so it could be that we have some significant storage of water ice on the moon's poles. The reason why we care about this is because, one, water is important to humans. We need that in a daily life. But we can also use that water, breaking it up into hydrogen and oxygen for fuel and for breathing. So this is a primary target of our next stages of exploration, is to see just how much water there may be on the poles. For me, as a geologist, one of the things that's very interesting is if we explore the moon, if we decide to build a moon base, one of the first things we're going to need is raw materials. And so for this, we turn towards basic mining engineering principles. What are the things of interest? And so again, with our different instruments, we're just now being able to tease out. What we're looking at right here is a color map that shows where the element thorium is high. So in the regions where you see it in red, that's where we have an enriched deposit of thorium in there. And we are able to tease this out for several different components. So this starts to build our mining map. Where would we go to get particular elements on the surface? Now, I started on Mars. It's by far my favorite planet. And in particular, the reason why I like Mars is that it reminds me of Earth. It looks like Earth without trees. And that in itself makes it an important area to study, because we can look at a planet and how it evolved without the major presence of life overprinting it. Of course, today, Mars has a very thin atmosphere. A lot of its atmosphere has been stripped away, and its surface is very cold and dry. But that wasn't always the case. We have a lot of evidence that Mars was once very wet. Not only potentially had large portions of its surface covered in oceans, but it had a thick atmosphere. It would have rained and surface water would have flowed on Mars in its early history. But the question we've been trying to answer for 20 years now is, where did that water go? There is quite a bit of evidence that as the Martian atmosphere was slowly stripped off by the solar wind, and it took a lot of that water with it when it did that. But there's also been quite a bit of evidence coming in the last 10 years that water may be frozen underground as aquifers. And combining this with the fact that we know that Mars is still probably warm in its interior. It has a layered structure, much like Earth, where it would have had an interior molten core, a mantle, and then a thin crust. Mars, being half the size of Earth, has cooled off a lot faster. I like to think of it as a giant baked potato and a little baked potato. I stuck them in the oven, and when I pull them out, that tiny baked potato is going to cool off a heck of a lot faster. And so we know Mars has slowed down, but the recent InSight mission suggests that there are still Marsquakes occurring. So there is still geologic activity coming in. So when we combine there may be heat and energy with there may be water, then we start to build up a habitable environment for this planet. Now, we'll say that Mars is by far our most explored planet. One of the most interesting things is it also holds the record for the most failed missions. Mars has not been kind to space exploration, but we're getting a lot better. We've learned lessons in every decade on how to do it better, starting back in the 90s when we sent a little shoebox Sojourner on there, all the way up to Perseverance in Jezero Crater today. And in particular, I'm sure many of our listeners have heard, but I just cannot I'm just so excited about the fact that Ingenuity has successfully flown around on Mars. Now, drones on Mars may not sound that hard, but we have to go back to the fact that Mars has a very thin atmosphere. So this drone had to be created to spin way faster with its blades in a slightly different configuration to even achieve this. But the fact that we have been able to achieve this makes our next wave of exploration all the more exciting. Now we've had this demonstration that we can indeed start exploring on right above the ground rather than from satellite. We can start exploring. And then finally, I just wanted to touch on the next stages in my career and for many of us, which is going to be exploring Europa. Now, Europa is an icy moon of Jupiter. It's roughly the size of our moon. And when we look at it, we know it's an icy moon, but it is crisscrossed with all of these fractures in what we in the scientific community call brown stuff.
This is a very technical term.
Yes. I mean, we have a little better handle on what that is, but in general, we have not yet had the capability to definitively say, what is that brown stuff? What we have recognized is that this darkish reddish material appears to be coming from the subsurface. It's coming up through these cracks or in large regions of chaotic terrain where it looks like the icy shell just kind of broke up and busted and this stuff came up from below. And so the idea that we might be able to sample or detect what was in Europa's ocean and it's now on the surface is of primary interest to us. Because again, much like Mars, Europa has some of the key ingredients to be habitable. We know that Europa's inner core is made of a rocky material, much like our moon, but it appears to have an ocean over it, and then at the near surface, that ocean is frozen. It's an icy shell. The tidal forces from Jupiter, much like we get tides here on Earth because of our moon, Europa is pushed and pulled by Jupiter, and that's generating quite a bit of heat. It's creating this liquid ocean. It's creating this, this interaction between the water and ice. And so we're back in the condition of where, when we think about habitability, do we have the ingredients there? We have liquid water. We have potential sources of energy, and we have the right chemical composition in those rocks to get there. And so the Europa Clipper mission is currently being developed. We have 2 instruments in San Antonio that will be flown on that. One is an ultraviolet instrument, and the other one is a mass spectrometer. The mass spectrometer in particular is one of the instruments that I've helped on. But in general, the plan for the Europa Clipper mission is we'll be taking a suite of 9 instruments. That includes cameras, again, of every wavelength. We also have radar, so we're hoping to sound that ice shell and be able to detect how thick is that ice shell, where do we hit that ocean. And in particular, we will be able to smell Europa. So there is some evidence in the community, especially from the Hubble Space Telescope, that Europa may have active plumes going on it. It's tantalizing, not definitive, but we want to be prepared. If there are plumes, we want to be able to characterize them. So we'll be able to look at them, smell them, and hopefully analyze them when we get there. And
fantastic, Dr. Wyrick. And if I can ask a couple of quick follow-up questions before our next guest comes on here. First of all, I'm fascinated by the deep planetary activity that you've described about the heat and the core of the inside of the planet, and about how on Earth, of course, volcanoes became a building block of life here. You wind up having all this you'll create the water out of the burn off of the volcanic activity, and so when you ask the question, where did the water go on Mars? I mean, is there any evidence that you find that there is something that could potentially be created in the future from potential activity in a planet like that, whether it's Europa or Mars?
You mean for humans or for life in general?
Life in general, just
Indeed. I mean, in Charity Phillips-Lander will discuss more when she talks about astrobiology, but one of the key things that we're looking for is the critical elements of carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. We know that all life here on Earth utilizes those key elements, but having that in the potential for energy. So energy can come from a lot of places. It can come from the sun. We remember photosynthesis from school. But in particular, it's chemiosynthesis that in the last 30 years we've really gained a lot of knowledge on. So when we talk about volcanoes under the ocean here on Earth, and they create these whole communities around them, the entire ecosystems, those ecosystems at their base are depending on chemical energy. And certainly in a place like Europa, there is at least the strong suggestion that chemical energy could be available to microbes. And then the third possibility of energy is that internal geodynamic heat. And so if you can heat that, you've got a source of energy. So it's certainly for Mars and Europa, it appears that we have the conditions for habitability, those major resources. The question still remains of, did life arise there, and how would we detect it if it did?
Okay. Well, thanks so much, Dr. Wyrick. We appreciate your time today, and you'll be back for the roundtable Q&A at the end here as well. So thank you very much. Next, we're going to have Dr. Charity Phillips-Lander that Dr. Wyrick referenced. She's a senior research scientist at Southwest Research Institute. As an interdisciplinary scientist, she draws on microbiology, organic and inorganic chemistry, geology, and material science to assess the habitability and biosignature potential of other worlds. Her research helps determine the vital role microorganisms play in altering geologic systems and how we detect evidence of life, if present, on other planetary bodies. And I love this other quote you have on your website, Dr. Phillips-Lander. We're all naturally scientists. Our first learning experiences in life are all hands-on, trial and error, which is an essential part of the scientific process. Welcome, and we look forward to hearing from you today.
Thank you so much. I'm really, really excited to be here today. So I am an astrobiologist, and I came to that sort of by the Forrest Gump method. I started out as a volcanologist and structural geologist like Danielle, and I was super interested in seafloor rocks, and I was like, man, if I could ever combine this with microbiology, I'll go do that. And then in grad school, I found out that was actually a thing. And so that started me on the trajectory of eventually coming to astrobiology, because as I was finishing my PhD and we had found evidence of past water on Mars, I realized Mars was habitable and that there was the potential to apply all the skill sets I had learned about microbes in Earth's environments to actually move into looking for life elsewhere. But the search for life elsewhere has actually been around for longer than I've been on this planet. The first astrobiology mission was actually in 1976, so more than 40 years ago, and we went to Mars quite ambitiously and designed a series of experiments. So we were looking for evidence of organics and then gases produced by microbial metabolisms. But then we were also putting in labeled carbon-14 to see if it was taken up by potential life. Because at that point, our understanding of the world was that life was dependent on sunlight. And so we were thinking that we were going to look for photosynthetic microorganisms in the sediments on Mars. And we didn't get a clear detection of those things. And that actually made us all take a big step back, and that caused the emphasis on habitability. What are the real conditions that we need for life on another planetary body, and then how do we search for that? The year after the Viking experiments, the deep sea drilling program, which is now the International Ocean Drilling Program, which has a number of scientists in Texas that participate in it, was going around looking at the ocean floor. And when they were looking at the mid-ocean ridges, so this is where the plates are spreading apart and we're having volcanism, and that's what moves the plates around on the surface of the Earth, they found these hot springs sticking out of the ocean floor. This was like a massive change in the way that we thought about things, because when they sampled them, they realized they were full of life. Well, this is 2 miles below the surface of the Earth, so it's not sunlight that's causing them to be able to live. And it turned out instead that what was happening was the cold ocean water was sinking down into that hot ocean crust and reacting with it. And those chemical reactions and all that metal-laden water was coming out of these hot springs and actually fueling microbial life. And in fact, if you go and look around these hot springs on the ocean floor today, it's not just microbes that live there, but worms and crabs and all kinds of life. And this fundamentally changed how we thought about everything. And that set off the next 40 years of exploration on Earth to really understand what are the limits of life. And it turns out that it's actually really hard to find a place on Earth that life doesn't exist in. And so even in the course of my career, So my PhD work, I actually worked in the Los Pilos hot springs, so that's the upper left-hand corner for people watching. And you can see these green bits all over it. That's actually microbes living in the hot springs in Costa Rica. So this is 90 degrees C, which is about 194 degrees Fahrenheit. You could literally cook your dinner in there. I wouldn't recommend it. It would taste terrible because it's very sulfur rich. And it's also a very low pH environment, pH of 2. And in fact, when we look at the limits of life, we find that microbes even live in negative pHs, like the Rio Tinto acid mine drainage. So it's very, very hard not to find life. And then at the other end of the pH range, you can go out to Mono Lake in California, which has a pH of 10. So if you're into alkaline water, that's about the same pH. And we found that in those tufa rocks, so these are carbonate rocks precipitating from the lake there, we actually find tons of microbial life at this very high pH environment. So they're spanning the entire pH range. And at the same time, we know that microbes live in hot springs. I've talked a lot about that. But they also live in frozen conditions. And so the bottom example, if anybody has gone hiking up in the mountains at all, you'll find these watermelon dustings on the snow, and that's actually snow algae. And so their pigments in the algae actually make this watermelon colored snow. And in this case, it's showing red, but you also get green algae on these surfaces. And if we go even more extreme, we could go to Antarctica and you can actually find microbes that are living in even colder and drier conditions. And there's very few places where essentially life doesn't exist. But one of the things I'm working on now is lava tubes. So these are formed when a volcano spews out lava, like in Iceland, the one that's erupting right now, or Kilauea in Hawaii. As that lava flows across the surface, the atmosphere is very cold, the lava is very hot, so it forms this solid rock crust because it's cooling very rapidly at that surface. And then the lava drains away over time, and it leaves these huge spaces. And eventually, groundwater or water from the atmosphere will actually come into the cave and can either be present as a liquid or as a solid. In this case, the entire bottom part of that picture is actually a sheet of ice that covers the entire bottom of the cave. And this turns into a habitable environment for microbes. And we see lava tubes on Mars that form just like the lava tubes we see on Earth. And we know from modeling work done by a number of scientists, including Kai Williams at the USGS, that we see ice is potentially able to accumulate in these lava tubes on Mars right now, today, in which case that's an active, habitable environment. So to Danielle's point, where did all that water go? Some of it's in the subsurface right now and acts as a potential habitable environment for life. But life detection is really, really hard. So the reason we haven't attempted another astrobiology mission is that first we had to define life, but then we had to come up with the tools of what to look for when it comes to life. And so the guidebook that we use right now was published by my friend Mark Nouveau. He's an amazing guy. And it's called the Ladder of Life Detection. And it goes from habitability being that bottom rung, you have to have a habitable environment first, to things that we call suspicious biomaterials. So these are like biofilmy type looking rock fabrics, metabolic byproducts, so things that microbes precipitate as a result of their metabolism, and then potential organic molecules that we know are produced by life on Earth, but could also be produced abiotically. And then it gets more complicated as you move up the chain towards things that we would be like, yes, I will hang my entire life and career on this being life. And so you get into chiral molecules, because we know life on Earth tends to have molecules that are ordered in a way that they tend to be handed. So you can have left-handed molecules or right-handed molecules, but life on Earth tends to all use the same handedness of molecules. And then you get into things like DNA and RNA, which on Earth we think of as very obviously being life. You know, DNA is integral to who we are. We use it on CSI to, you know, identify people. And then we look at things like those labeled substrate experiments and things like that, where we're looking at active metabolisms and evidence of that metabolism. And finally, we get into growth and reproduction, and mobility goes into that role, where if we melted a sample of Europa's ice and looked at it, will we see microbes swimming around in it? Would they be actively reproducing? And then ultimately, do we see a change in life through time? That one's pretty difficult to actually see in the course of a planetary mission. And taking that, we've gone and we've started applying that roadmap, essentially, to a variety of planetary bodies, including ocean worlds. And so in ocean worlds, we know we have this ocean. We know we have this energy available from hydrothermal circulation. We know, in the case of Enceladus, that we have these active plumes venting out that we could actually sample. And so when we sampled them with Cassini, we actually even found organic molecules, which are indicative of the potential for life. So all the ingredients are there, and it's about figuring out whether or not life is there. And so we finally come full circle about 40 some odd years later to this question again. And so we haven't flown another astrobiology mission yet, but we have a number of concepts in development. And so following on to the Europa Clipper mission, which is selected, one option that we have moving forward would be the Europa Lander concept. So this is an idea that scientists are working on to try to develop for a future space opportunity. And they're looking at a wide suite of biosignatures, including that growth and motility, the handedness, and then also all those more suspicious biomolecules that would also lend support to that evidence of life. And on the other side, we have multiple opportunities to look at Enceladus. And so we have the upcoming New Frontiers mission proposal call, which would select potentially a smaller Enceladus mission to target some evidence of life and also evidence of habitability. And then we have a flagship mission concept like the Enceladus Orbilander. This is coming out of APL, but a number of people at SWRI, Southwest Research Institute, are actually on that team if it were to be selected. And they're targeting almost the entire suite, everything but that Darwinian evolution, to look for life. And then if we look further afield to Danielle's favorite planet and one of my favorites, we have multiple opportunities that are both current and future that are going to target the search for life on Mars. So Mars 2020 right now is scanning around Jezero crater, right, looking for biosignatures, so this evidence of past life. And they are going to be cataloging samples. And yes, they've run into a little trouble with their first one, but they're going to get this. And they're going to leave those behind for Mars sample return. And sample return missions are really great because they give us the opportunity to pick up all those samples, bring them back to Earth, and where we can only select a handful of instruments to go to a planetary body, we have almost unlimited instruments here on Earth to answer those questions. So it gives us a lot more ability to interrogate those samples in detail. So the Mars sample return mission will fly probably sometime late in the next decade and pick those samples up and bring those back to Earth, which will give us an unprecedented opportunity to know Mars better. And at the same time, we have the Rosalind Franklin, so that's the ExoMars rover that's getting ready to go to Mars now, and it has a deeper drill than the Mars 2020 mission, but it's also looking for signatures of life in the near surface. And so both of those will provide a lot more information, not just about kind of the water history of Mars, but also that potential for life to have ever evolved on Mars. And then looking forward, Danielle and I, as well as a number of people around the country at various NASA centers and universities and even the USGS, have been working on one of many concepts to explore the subsurface of Mars. So in 2019, the National Academies came out and they said that the subsurface of Mars is like the best place to look for life, and that we should start really focusing on that and developing concepts for that. So we have developed kind of an idea of how you would do that. Again, this isn't selected, so this would be something that, if you're excited about this right now, we'll be working on and trying to get to a point where we can propose it to NASA. But we would be looking at the chemistry and habitability of those lava tubes, like I've been studying out at Craters of the Moon National Monument, but looking at them on Mars, both to understand the habitability of those lava tubes and then the potential for either extant or past life. And so that's something we're working on. One of the key things that we are working on right now is that I feel like the science is actually pretty robust on how, life potentially being in these caves. But the challenge is really engineering. And so we have a lot of these structures where how you get in is vertical. And that would be very, very hard for a robot like even Perseverance, which can drive around. It might be much easier for something like the helicopter if it was small enough. And then we have some that are horizontal entrances, which obviously you could drive right into, which would be much easier. And so we've kind of looked at all the different options that are out there right now to figure out how hard would it be to get it in the cave? What things would we need? Could we attach a tether to it to get it down the steep drop and then allow it to wander around on its own? Would we just drop a bunch of things in there and let them scatter out and sample? Could we fly something in, but then maybe we wouldn't be able to put that many instruments on it because there isn't that much atmosphere to support a big payload? And so this is all like engineering questions that we're actively going to lava tubes on Earth and trying different things out to figure out what's going to work the best. And at the same time, we have software engineers who are figuring out how to get it to move around, sample, make decisions for itself, and communicate back to Earth largely autonomously, because unlike Mars 2020, we don't have that direct link back to Earth because you're underground. And so how do you overcome that communication and allow it to make decisions when you may not be able to see right away what it's looking at? So a lot more of that machine learning and AI stuff that's coming into being right now will fuel this mission concept as it moves forward. So there's a ton of opportunities for anyone who is interested in space exploration, and this is just a handful of the things that we'll be working on over the next decade as SWRI. One other thing that we're starting to tackle is this human exploration component, and from my perspective, I'm really interested in, some microbes are beneficial, and some are not, as we've all learned over the past year and a half. And so one of the things that we're really thinking about is, as humans go into these different environments, as they explore throughout the universe, how do we keep them safe? And so while we're looking for life to understand if we're alone, we're also looking for life to understand how we protect other people moving forward, so that no matter where you are in the solar system, you're safe.
All right. A quick follow-up about the lava tubes, of course. Better way to explore the underground than simply drilling, of course, right? Because they're already you're
right. The access point is already there. So we've seen some challenges with the InSight drill. So there's because lava tubes provide this natural access point, we can just take advantage of the fact that there's already a hole in the ground for us to exploit. And that works well for both humans and for robots. So eventually, human exploration could take advantage of lava tubes as well.
I read somewhere when you talk about life and how it works in space and on other worlds, that I think SpaceX and NASA were launching some tardigrades and other very small creatures in earlier this summer. Do you know anything about that? And also, this may seem like a really silly question, but is there any reason why we would just dump a bunch of tardigrades on the surface of the planet and say, okay, because they're really hardy little tiny things.
They are incredibly hardy. So NASA is doing a number of different experiments. Tardigrades are just one example, but they're looking at a variety of microbes in space environments to understand how their behavior changes in space. Do they change their habit? Do they evolve pathogenic traits? Do they, what do they do? Because we don't actually know. But tardigrades are really interesting because they're so robust to so many of the conditions that we observe in space. And but the challenge and the issue that we have in exploration is that we don't want to contaminate surfaces with our life. In fact, I would argue the moon
is like the prime directive type thing.
Already contaminated because we dropped off astronaut poop on the moon's surface back during the 60s. So we're running an active, potentially astrobiology experiment on the moon right now. I would actually love to get a sample of that, not gonna lie. But yeah, our goal is to protect the life elsewhere so that we can characterize it. But eventually when humans show up, you're gonna interact with that life. And hopefully it's not Jurassic Park style.
Somebody asked what in the chat here, just as out of curiosity, again, when we talk about conditions, what are the average temperatures on Mars again? Dr. Wyrick mentioned it, but
it really depends where on Mars you are, but temperatures can get up to about 25 C, which is very much like a nice day in San Antonio, maybe in the fall. Not so much right now. And then it can get quite cold, so more than 15 degrees C, below zero. So it can get quite cold. And in fact, craters of the moon, one of the reasons that we use it as an analog is because it overlaps with those temperatures that we see on Mars. And so that makes it a really great analog when we're looking at the lava tubes because they're getting exposed to that same kind of temperature fluctuation.
Right. Well, Dr. Phillips-Lander, thank you so much. We're going to bring up our next guest, and then we'll have you come back here at the end when we go to our full panel for questions. And a reminder that if you have questions about anything that you're hearing today, or if you have questions about what might be in the future, please go ahead and type them in the chat window on Facebook Live or in the YouTube link. If you're looking at it that way, type it in the chat, and at the end after we're done with our full presentation here. And now we look forward to the future of our presence on other worlds and frankly some amazing and imaginative engineering with Sam Ximenes. Sam Ximenes is a space architect with over 30 years of experience in the aerospace industry with NASA, the Department of Defense, Lockheed, and international space programs. He's held executive management positions at Lockheed Martin, L3 Communications, and the Futron Corporation. He's the founder of the WEX Foundation, created to promote STEM education in schools to nurture future space scientists. And he's currently CEO of XArc Exploration Architecture Corporation, a space architecture consulting firm he founded in 2007, based here in San Antonio. So welcome, Sam Ximenes. Thanks so much for being here. I'm really excited to see what you present today. Some fascinating stuff that folks are going to enjoy seeing, I know for sure.
Thank you very much. I appreciate to be here. It's really exciting, actually, to hear the scientists. Aren't they great? They are my favorite people. That they go into these different worlds and look for the microbial stuff, and it really gives you a sense of what we're doing in terms of exploring the universe. But what I want to talk to you today about is how the practicality of that, and what does it mean for us as humans. And when we talk about habitability, in my world, I'll talk about human habitability. How do we live on a different planet? What I want to talk to you today about is three organizations, as you mentioned, XArc, WEX Foundation, and another one called Astroport, and what they're doing here in San Antonio to advance space for San Antonio, and how we use that for providing a space community for San Antonio through our STEM education programs. So XArc, just to give you some background on that company, is a space architecture company. It works in three different domains of space architecture. Planetary surface systems. Those are the habitable surface infrastructure that you need to do to build habitats and landing pads and all the surface systems that go into that. And then there's orbital architecture. This is the architecture that's in orbit, the space stations. And then we have these space here on Earth architecture, which is spaceports, for example. facilities that support spacefaring activities. So XArc is involved in all of that. And I bring that up because XArc has been involved with the spaceport development here, the commercial spaceports that have been coming up. You saw where a couple of weeks ago Richard Branson went into space.
Yes.
That facility was one of the projects we worked on in New Mexico, the terminal hangar facility. And then we also were part of the Houston Spaceport, which is also developing their own spaceport capability. And from there, we take the knowledge we gained from all that to learn how do we build a spaceport on the moon, essentially. So this is why we created Astroport Space Technologies, to develop the technologies now to build and understand how that can be done by using the in situ resource utilization, the ISRU, they call it, which is taking the resources from the surface, the moon, the regolith dirt, basically, and how do you turn that into construction material. So you can consider XArc as the architects and Astroport as the civil engineers for the construction aspect of it. And we've been looking at, again, some unique technologies. I'll talk about that later on in the presentation. And then the third one is the WEX Foundation. One I'm more proud about is that we are using this as a way to build a STEM educated workforce for developing careers in space. And we use the activities of XArc and Astroport as the framework to give our students that in our programs real hands-on projects to work with and help us solve some of these problems, some of these issues, these technology development issues as well. We received some funding from NASA to do that here locally. They liked the program. They gave us some more money to take the program national with the new Worlds Await You program as well. So what are we about? So we were talking earlier about lava tubes. Our whole focus there in these technologies we're trying to develop is how do you actually get into these lava tubes in these pits, especially on the lunar surface and on Mars as well. We're looking at what we call skylights, pits, and tubes that are on every planet. Here in the corner, you see the largest one we have on Earth, which is in Vietnam. And that's about the size we think that these lava tubes are at in terms of volume on the moon, and probably twice that size on Mars. So when we look at that, we decided that there was a spot that we wanted to really focus on that was discovered about 2007 called the Marius Hill Skylight. And it is one of the first pits, well, it was the first pit that was discovered. And we think that this is a good candidate for understanding the habitability of that location for human settlement, eventual human settlement. How do you use this in such a way that we start mining the surface of it and start developing this pit in a way that it can be a settlement base for using the volume of the pit for maybe at some point in the way distant future, putting a dome on top of it, creating more atmosphere so you can get out of the cans, get out of the spacesuits, and have more room to move around in as well. So the objective then is to understand what are those, as an architecture perspective, what are the pieces of that to go into the overall settlement itself. You have a spaceport itself being developed, and you have to have a location for that, and then you have to have it protected for the coming and goings of the spacecraft, so it doesn't disturb these assets that are already in place there with the rocket blasts. And then you have to have the mining for surface area, and then storage for all that volume that and processing that you're doing for the fuel consumption. You need a power source, and you need, of course, the actual construction activity that goes into building out that pit for a long-term stay. So we take this in terms of what we call the Lunar Ecosystem and Architectural Prototype Program, or LEAP-2. And we look at this in terms of how do you take these technologies from the very beginning of the remote sensing piece frame that we use at the very beginning to characterize the site, and we use a timeline for that. The timeline's a little tricky sometimes. We don't really, have to stick to it because there's always policy changes and whatnot. But in the very beginning, you talk about remote sensing. You have to characterize the site, understand what's there. The next phase would be the reconnaissance phase. This is the robotic reconnaissance part of it, where you send the robots there to try and get down into the pit and do the characterization and the remote sensing that way. And this is probably happening within this decade, I believe. We'll start seeing the first robots getting into these caves. The next phase would be then the human reconnaissance part of it. How do we get humans down into the caves, into these pits, and then ground truth what the robots found to understand, does this particular location really fit the bill in terms of being able to build out a big infrastructure, and it has the right things that we needed to look for in terms of the survivability within the cave itself. And here we have technologies that are being developed for short stays, three days at the most probably, maybe a month at some point when we get to the next phase, which when we start building little more habitable volumes inside their habitats and whatnot. And here again, these are different technologies that are being developed for that part of it. And then finally, by the mid-century, we think that we'll start thinking that well, this is a place that we want to start putting larger volumes for people to stay there, and start clearing out the cave and getting more infrastructure for coming in and out of it. And then maybe by the end of the century, we finally have a full-blown settlement there and we have a dome over it. Now, every one of these phases, there's technologies that are all unique to it. And we have a consortium of companies that come and help us out, and they are working with their own R&D programs to develop those technologies. So, to talk about what some of the things that we're doing with that, one of the first things we're trying to develop is what we call a lunar dust measurement instrument. The dust is probably one of the biggest constraints we're going to have to understand and overcome, because it gets into everything. It's harmful. It's fine powdery, almost like talcum powder, and it gets on suits and the gears and into your lungs as well. And one of the things we, from an engineering perspective, is to understand dust accumulation rates. For example, how much dust will accumulate over time on your solar panels. And this little instrument just fits in the palm of your hand. It's developed by students here in San Antonio, started at middle school grade, and went on to undergraduate students, and are using this as their first payload to the moon. We're trying to actually get this device on the lunar surface.
Wow.
On one of the NASA Phillips-Landers as well. And we're applying for funding for that as well. So we're at that stage now where it's actually at the flight hardware portion of it. Other things we're doing is looking at I mentioned earlier, the ISRU technologies, the in situ resource utilization. How do we take the lunar dirt, turn it into a hardened material, and for construction applications? And we've been doing tests on some of these melting technologies we're working with. We've got a way to melt the technology. This is something that NASA actually funded us to do, is to take that dirt, turn it in, without any additives added to it. You melt it and you turn it into a brick, and you can make landing pads out of it or roads and whatnot as well. Another part we're doing is taking the same dirt, and then we add something to it called like a plastic, and we turn it into a filament that can be 3D printed through the extrusion process. So now we're using that for habitats, and because it's got the plastic in it, it provides additional radiation protection within the habitat structure itself. This is a little bit more tricky. It's not really a true ISRU because you have to import the binder that you need to use to make that filament. But at some point, we'll be able to make farms, greenhouses, and produce this with biomass that turns that filament into that plastic that we want to have. That's way down the road, but that's a possibility of what can be happening in terms of a true ISRU application. So at Astroport and WEX Foundation, we're looking at the habitat designs that we're working on, taking robots and using 3D printers and developing those as well. This is all happening in San Antonio, at the port San Antonio right now. From middle school to high school level education is going on. We have a test bed at the University of Texas at San Antonio at UTSA, where we have a mock-up of that lunar pit, where we have our students develop robots and concepts for how to get down there, and with various different ways. And they're also looking at the idea of the construction of the landing pad. This is a picture of our concept for one of the first things you need to do when you get to the lunar surface is build a landing pad. The landing pad is the first infrastructure that has to be put in place, because your coming and goings of your spacecraft, we're going to be blasting out all this plume exhaust and debris, and it could be detrimental to other assets you have already put there on the lunar surface as well. Here's another technology we're working on is a regolith compressor. Again, a student program where we decided that we need to do the first preparation of the underlayment of the landing pad. You have to press down the regolith and then we have to figure out how that's done in terms of robotic machinery. This is all autonomous. We have to be able to work with. This one is was what NASA gave us some money to start working on this year. It's our lunar furnace melter. This is where we take the regolith and we melt it, and now we're combining it with a nozzle that is a one-step process. Essentially, we accumulate the dirt, we put it into the feeder, it melts, and then it forms this brick, and then it places the brick at the same time, all in one step, so that you can just digitally put bricks that pop them into place and build out your surface, your foundation, or your landing pad. And we're working on different technologies, from the 3D printers to laser seaming of surfaces, and also looking at some work we've been working with in previous years with Southwest Research Institute, understanding the volatiles that are in the regolith, so we can do additional extraction of these minerals. It's not just for printing. We can actually take the same regolith and pull out the oxygen or titanium or magnesium that's in this regolith, in this dirt, and use that as additional construction material. And so we're talking about access to the pits. Here's a lunar pit concept we have for using a zip line, for example, taking a zip line and shooting it with a harpoon cannon, essentially, and throwing it. One of the first ways to get access there is to put a line across the pit and get into it by lowering your down that zip line with your instrument. This is a mission we have called the LIDO mission, and it is using a method of what we call green reconnaissance. So when we land at this pit, we don't want to contaminate it. We don't want to be able to have it the science disturbed because of the blast from the rocket engines flying too close by and disturbing the environment before we even get there. So we land further away, about a kilometer away, behind some high ridge area, and then we traverse to the pit, and then stage the robot there and shoot the zip line across, and then lower our payload instrument suite down using these legged rovers. So now I'll talk about habitats. These are some habitat designs we've been starting to look at in terms of Mars construction. It's one of our first concepts for 3D printing the habitat, where we again start looking at something different in terms of the ability to make these structures not so standardized, but have a little bit more creativity in the way you make these designs. It was really more of a study in terms of the volume concepts of how do you put 4 people to live in one of these things over a year period of time in a confined environment, and what those volumes are looking like for the astronauts. This was called Archab. One of the last ones recent ones we did was called Hexab. This was when we started really looking at 3D printing and turning that into the ability to actually make the technologies that go with that. This was a concept that we really looked at it in terms of the overall construction application, from outfitting it to the interior. What would the interiors look like, and how do you live in there? From the workspace to the common space to the greenhouses and to the crew quarters as well. We had to look at it in the end-to-end system, the way you put all the hardware that goes in there, the HVAC they call it, the MEP, the mechanical and electrical and plumbing. How does that get outfitted into it? It's one thing to just print out a habitat and a structure and a shell, but then how do you outfit these things? It's very complicated. And that's probably not going to be the things you can make on site. You probably have to bring a lot of this with you. So these are trade-offs that has to be put together in terms of the ability to 3D print or make it more modularized with already built-in components. The other thing we had to look at was the constructability of it. How do you construct this thing? What's the process for constructing it, and what are the ways that it gets built out by using on Mars? I mentioned that we would combine our filaments with a PLA. Well, on Mars we can take the atmosphere and produce the PLA out of the atmosphere. With the carbon in the atmosphere, we can produce the plastic and combine it with the dirt to make the habitat extrudable material. And then we had to look at what's the constructability of it, what's the phases of the construction process itself, how long does it take over a period of time. In this case, it was a 6-month process for this thing to be built, one unit to be built out, and based on the way we were doing the construction process. So, other things we're doing here is looking at how do you get these modules inside the caves. Here's something where we're taking tubes that are inflated out. This is a process where we compact the module and then expand it out with some inflatable tubes to make the floor system. Again, looking at the relative porosity of how do you make sure that when you start putting these domes over these pits, that you don't have leakage from the atmosphere. And you're going to need a lot of atmosphere, by the way, for these pits to get, if you want to cover them up, because in the case of the Marius Hills pit, it's 132 cubic meters of volume, almost 85,000, pit volume for air that you need to put into it as well. So where do you get all that air? How do you create that, and where does it come from? So let me go to the last part here is the LCATS program. This is our WEX Foundation program here in San Antonio. It's a community program. We have a lot of partners involved in it. And this is where we take what you saw previously, all those technologies we're trying to develop. We give these over to the students as well to look at, to help us figure out, some of those challenges, and they come up with other unique ideas on their own. So our LCATS program is called Lunar Caves Analog Test Sites. Here we take students into local caves around the area. They design science instruments, design robots, and then they go into the field and do field tests in these cave environments as well. As part of their experience. The idea is to give them a 3-year experience. For the first year, they're doing that remote sensing program that we talked about, and they're learning about that. And with high altitude balloon launches, where they put their sensors in those balloons and they learn about the atmosphere in that way. And then the second year, they're in the robotic part of the program, with the reconnaissance phase, where they're building the robots and doing the reconnaissance. And then the third year, they are doing the space architecture, learning about space architecture programs as well. And then finally, the fourth year, they take all that experience and they turn it into a comic book. We are proud to say that we just published our first comic book this summer, and this is a kind of I guess their engineering journal, if you will, in terms of the storyline that they put together over how they see the exploration of their venture there. Like I mentioned earlier, that the lunar dust instrument. This is the way that we developed that lunar dust instrument. It began with middle school students, and they went through the cave environment. They went through habitat design, and they also did launches and balloons. And then now we're at the point where, again, we're trying to get this little instrument on the lunar surface as well. With that, this is the end of it here. I'm just going to show these slides. This is the build-out phase, where you go into one of these pits. You put some way to get down there. In this case, it's a zip line, and you lower down into it. And this is the first parts of it, of your exploration journey. You get down in there, you see what's down there. You camp out, for a few days, figure out the environment, get there later on, and then by the time you get to the end of the century, you start building it out. By the end of the century, we're back to the point where we're actually building out the habitat.
Wow.
In summary as well.
Fantastic. Sam, thank you so much.
Thank you very much.
First thing I wanted to ask you real quick, and we welcome back Dr. Charity Phillips-Lander and Dr. Danielle Wyrick here. We'll take just about 5 or 10 minutes at the end here for questions, not only from myself, but also from you. If you have any particular questions, please go ahead and write them in the chat, and they'll be brought up to our panelists here. The first thing I wanted to ask, because you talked so much about students in your presentation, Sam, is, if a child, or if a parent of a child is interested in learning more about WEX Foundation or about the program, and what are the first steps that they need to take, and also what are some of the schooling, what are some of the courses and what's the avenue that a person should be directing themselves towards?
So the first thing they can do is actually go to our website, wexfoundation.org, and there's an application that we're taking our first cohort, or next cohort of students in for the fall semester, which will probably be in October timeframe. So you can apply right there for that. We began the program by actually focusing on students that were already STEM oriented. They already were interested in STEM careers. And we plucked them out of what's called the San Antonio Prep program, where it's a summer program that they were already entered into through UTSA. And they had to compete to get into the program in the first year. And so they were the best of San Antonio. And they then committed to an academic year of 16 Saturdays over the fall and spring semesters. And those students then were well motivated to already go into a careers in space. Mm-hmm. Now we're focusing on trying to get students that have no STEM experience or have not been exposed to it, and reaching out to them into the demographic areas of San Antonio that are more challenged for getting students into technology career paths. And now we open it up to anybody who wants to come in, and we'll tutor them by giving them the right background in terms of the science and technologies and mathematics that they need to have to help us and be successful in our program as well.
It seems like the common thing that I've seen in all three of the slide presentations we've seen today are these lava tubes, the caves.
Yeah.
The thing, a right place for exploration. And it seems also that an example of a collaboration between industry and between the science comes with the development of ways to, like you said, how do we get down there? How do we find this? Is that right, Ximenes?
Yeah, I
Absolutely.
mean, we have NASA also funds a virtual institute that is looking specifically at geophysical investigations. So the cool thing about these lava tubes is many of them do have skylights. So that's an obvious, there's the hole. But a lot of these tubes have not collapsed, but the hole is still there underground. So how do we find that? And the answer there is a variety of geophysical instruments, whether that be a ground penetrating radar or some other magnetometer or something like that. These are tools that we use every day as geologists here on Earth. But how do we take that and put it on the moon and lay the groundwork so that we can tell someone like Sam and his team, here's the best spot to try to build that. Right. And so to your point, like, what do you study? I would argue study what interests you first, and there is an application there.
Mm-hmm. I'd like to talk more about that. I think that any profession that you are interested in can be applied to space. If you want to be a chef, go to the Culinary School of Arts here in San Antonio, learn about chef, and then learn about space food. Yeah. How do you grow food in space? How do you eat in space? You want to be a lawyer? Go to St. Mary's University here in San Antonio, learn about law, then become a space law lawyer. Mm-hmm. Learn about that. An artist, you want to go to art, become an artist, go to the Southwest Art Institute, learn about art, then become a space artist. We need every profession, every career in space exploration at this point. Anybody can join space exploration.
You've talked about San Antonio being a possible place for being a real hub for the space industry. Is this? And you're kind of encouraging that with those comments, and I think that's a way to look at it in a new way, that every profession can be a part of it.
We have it all here in San Antonio. The cybersecurity part of it, the construction part of it, it's here in San Antonio. San Antonio can be a real hub of space activity. And I like to see San Antonio actually be known for specialties in it. For example, space construction would be a good way to make a niche in that community as well.
One more thing about the lava tubes too, and again about habitation. Would that be an ideal place? Because I saw some examples in your slides of above surface structures, but in order to protect from radiation and from space, do lava tubes seem like an ideal place actually for building on other worlds as well?
It's probably one of the better reasons for it, because the protection of the radiation, the micrometeorite bombardments. Yes.
And I think Charity said it well, that these holes in the ground are already there for us to take advantage of. And so there are a number of different organizations trying to figure out, how do we characterize them? Because right now all we see is a hole on the surface, right? It's very difficult to know what that might look like underground. So there's quite a few of us that are trying to look at natural examples here on Earth and trying to understand what is their extent, how tall, how long. But also, throwing it over to Charity again, what's in those caves? What is there water? Is there microbes and all of that? And so I think there's still a lot we need to understand for lava tubes here on Earth, because those are easier for us to access. And then how do we translate that to the Moon and Mars, where we're pretty sure that they exist there. And definitely I think it's an easier target to achieve if we can get into that tube rather than having to dig a hole underground.
Yeah, Charity?
Yeah, I agree with Danielle's comments. I think one of the things, too, that we need to think about is these are natural places where resources are accumulating that are available for humans to potentially use. I mean, we talk about water ice as a habitable environment for microbes, and that's exciting, but also it's something that we all need to live. And so to Sam's point, this in situ resource utilization part also comes into play with lava tubes.
So we're run over time a little bit, but I just wanted to give us time for these questions here. So I want to ask one more question, and I'm a movie guy, so I got to bring in a movie, of course, which is The Martian, the movie, right? And in the movie, we've been talking about water and development of water and stuff, and I want to know, in that movie, Matt Damon's character devises this method of producing water by burning hydrogen and creating water vapor. Would that work? Is it practical? Can we do that on Mars?
I whether it's practical, no. if it was my life and death, I'd certainly give it a try.
It was for him.
Yes, it was practical for him. I think that there are a number of different ways that we will be able to extract water on Mars in particular, even on the Moon in those permanent shadowed regions. What we don't understand is really the nature of that ice. Are we talking about
what's in it? What's it made of?
Well, are we talking about a solid block of just ice, or are we talking about a whole bunch of dusty dirt, the regolith, that has just a microscopic ice in the pore spaces? I need two different techniques to mine that water in that way. And so that's part of what we're really trying to understand at this stage, is what is the form of that ice? And once we can kind of understand that, then we can potentially engineer a way to mine the ice out.
Well, I want to thank all three of you for being here again today. Dr. Charity Phillips-Lander with Southwest Research Institute, Dr. Danielle Wyrick with Southwest Research Institute as well, Sam Ximenes with XArc Exploration Architecture Corporation. Thank you very much. I want to remind everybody that the slides from today's presentation will be posted on our website later on the post for this particular event, and the video from Facebook Live as well as on YouTube will remain as well, so that you can share it with a family member or a friend. We want to thank UTSA, Knowledge Enterprise, and Port San Antonio for their support of Think Science. And our next Think Science discussion is coming up in November. We're going to be learning about the science of music, how it works, how we as humans respond to it. I'm Nathan Cohn. Don't forget to listen to Science Friday with Ira Flato every Friday afternoon from 1 to 3 right here on Texas Public Radio. I want you to stay safe, keep wearing your masks indoors for safety, and we'll see you soon. Thank you very much.